Okay, so in the previous video, I showed you how to do basic truth tables, right? You just lay out the possible combinations of truth values for the individual sentence letters, and then you start filling in the remaining columns in the order that the connectives were added when you were building up the sentence using the recursive definition, so that by the time you fit the last column you add is the main connective for that sentence. So in this video, I'm going to talk about applying truth tables. And what this means is that we can use the truth tables to show us logical properties about sentences and collections of sentences. And we're going to take advantage of the fact that that main connective is the last column that we added, right? And so by looking at that last column, we're going to be able to identify these various logical properties. So the thing you have to do is go back in your mind to chapter 3, when we talked about all sorts of additional logical properties that we were going to need for formal logic. And the first set of them was contradiction, tautology, and a contingent sentence. So we said that a contradiction is a statement that cannot possibly be true because of its logic. A contradiction is something that must be false. And we talked about ordinary English examples of this. So if I say he is both running and sitting still at the same time, I have contradicted myself. That is a statement that has to be false because of its logic. The colorless object was bright green. Contradicts itself. The circle had sharp corners. Contradicts itself. And on the test as well, you had to identify ordinary English sentences that were either contradictory or tautologies or contingent sentences. So now we want to identify contradictions in our logical language, SL. So a simplest example here is going to be this sentence, A and not A, right? If you say that just in English, it already sounds like a contradiction, right? A is, it is raining. So it is raining and it is not raining. That's a contradiction. Now let's think about what is the main connective of this sentence and what is the secondary connective. If we were to build this sentence up, we'd start with the sentence letters, and we only need one. We just need the A. We can have a not A, and then we add an A to it. So the third level is where we have this sentence A and not A. And the and is going to be the main connective because that's the one we added last, and the not is going to be a secondary connective. So for this one, since there's only one sentence letter, there are only two rows, right? One for the case where A is true and one for the case where A is false, right? So we start out with a truth table that looks like this. We fill in the column under the negation, because that's the secondary connective, and that just flips the truth values. That one is false and true. And then we look at the column under the and that is false both times. In the first row, it's false because the right-hand side is false. In the second row, it's false because the left-hand side is false. So what we see here is that there are only F's in the column under the main connective. And so that's what we're going to say is the definition of a contradiction according to truth tables. If you draw up the truth table for a sentence and under the main connective there are only F's, you know the statement is a contradiction because no matter how the truth values are arranged for the individual sentence letters, the truth value for the whole thing comes out false. Now think about a tautology. Tautology is just going to be the reverse of that. A tautology is a statement that must be true because of its basic logic. All bachelors are unmarried men is a standard example of a tautology. It's a statement that's true by definition, right? An invisible object can't be seen. All triangles have three sides. These are statements that must be true. So if we want to do this with truth tables, we can imagine a sentence A or not A. Again, we only need 2 rows here because we only have one sentence letter. And for the for the next column, we're going to do the negation. That's going to be false and then true. And now for the main connective, we have an or instead of an and. And this time we only have T's under the main connective. So this is going to be how we understand a tautology according to truth tables. If there are only T's in the column under the main connective, we know the statement has to be true because of its logic. No matter how you rearrange the truth values for the individual sentence letters, the whole sentence comes out true. So the last kind of statement we looked at here was a contingent statement. And this was a statement that could be either true or false, depending upon the way the world is apart from the sentence, right? And so we just looked at examples here like, it is raining right now, or I am a bachelor, or this triangle is green. In all of these cases, the sentence could be true or false. So when we want to do a truth table for them, if we find that there are both T's and F's under the main connective, then we know the statement is contingent. So here's a simple example of a contingent statement, A or not B. And we start with the individual sentence letters, right? So A is true, true, false, false. B is true, false, true, false. We flip the B for the next column, and then we get the or statement in the middle, and we can see that the or contains both T's and F's under the main connective. So this is a sentence that could go either way. It's contingent. We also looked at logically equivalent statements. And 2 statements were logically equivalent if they had to have the same truth value because of their basic logic. And so often this is just things that are true by definition, right? So it is raining and water is falling from the sky, we're going to say are logically equivalent statements because it's just true by definition. Bob is a bachelor, Bob is an unmarried man. Those 2 statements have to be the same because of the definition of bachelor. So logically equivalent sentences effectively say the same thing, right? And in this, when we're doing truth tables, saying the same thing means always having the same truth value. That is, always having the same column under the main connective. So here 2 equivalent sentences, not parentheses A and B, and not A or not B. We fill in the basic columns, right? Then we do the columns that modify the columns that we just filled in. So for the sentence on the left, we filled in A and B. Those 2 letters are connected by the and. The and is the next thing we do. So it looks like that, right? And that's just the characteristic truth table for the and. In the other sentence, the or comes later in the order of operations. What modifies the initial two letters A and B are the two negations. So we fill those in, right? When we fill in the negation for the sentence on the left now, what we're going to be negating is the last thing that we filled in. So the last thing we filled in was the truth table for the column for the and, right? That goes true, false, false, false. That's the column that's being flipped for the negation, and so we get false, true, true, true. Often, the most common mistake I see people making doing truth tables is doing the columns in the wrong order, right? All right. When you go over here, the or is modifying what's on the two sides of it, but in that case, it's the columns under the negations because those are the last two we filled in, right? But it turns out that this gives us the same result. False, true, true, true. The first line is false because the two things on either side of it are false, right? You've got those two F's in the blue circles. And what that means is that the sentence not A is false and the sentence not B is false. And you just go down the column like that. Because the columns under the main connectives are identical, the two statements are logically equivalent. Next up was consistent sentence statements. A set of statements is consistent if it is logically possible for them all to be true. So we had a set of sentences like this, right? This shape is a triangle. This shape is red. If this shape is red, it must have three sides. Those sentences are consistent because triangles have three sides. If we change it to four sides, then the set is inconsistent because the first two statements imply something that contradicts the third one. So when we're looking at truth tables now, what we're looking for is a situation where all of the sentences that are true at the same time. So now consider these sentences: A or B, not A and B, and not A. We fill in the initial columns, right? Then we fill in the columns that modify the columns we just filled in. So that's the or and the not for the two sentences on the outside, and that actually finishes those sentences. For not A and B, we want to do the and first because the and is inside the parentheses. And then that's the column that gets flipped around for the last statement, right? Now what we can see is that on this third line, the truth value under the main connective for all three statements is true. That means that there's a possible universe where all three of these statements are true. So if you look at it, what's going on here is that this is the world where A is false and B is true. When that happens, all the sentences are true. Okay, the last property the last logical property we looked at was the most important one for this course: validity, a concept that I've been emphasizing again and again. So an argument is valid, remember, if it is impossible for the premises to be true and the conclusion false. So we can show an argument invalid if we can find a situation where the premises are true and the conclusion false. And that's just going to correspond to one line on the truth table. So let's look at a slightly more complicated example. A implies B, A implies C. Therefore, that symbol there with the two lines going off to the right is called a double turnstile. In this case, it means therefore. Therefore, B implies C. So this is an invalid argument. It looks like a standard kind of chain reasoning. A implies B, B implies C, therefore A implies C. But the letters have been mixed up so that it actually doesn't work anymore. This is also an argument with 3 sentence letters. So that means that there are going to be 8 rows on the truth table, right? And so let's just review how to fill these in when you do something with 8 rows. You start with the first letter, with A, and you do 4 truths and then 4 falses, right? So you split it in half. Then with the B's, you do units of 2. So it's true, true, false, false, true, true, false, false. You split what you had done previously in half. And then finally for the C's, it's just alternating true and false. Now in this case, when you fill in all of the truth tables, you see you have different patterns for the main connective each time. But look here on this row that's just 2 up from the bottom. You've got 2 truths in the premises. A implies B is true, and A implies C is true. But you've got a false for the conclusion. B implies C is false. And so that shows that the argument is invalid. Okay, for the last little bit here, I want to talk about some metalogical concepts, that is, concepts that explain about what we're doing. So we have a distinction between syntax and semantics, where syntax is just a set of rules for manipulating symbols, and we don't pay any attention at all to what the symbols mean. So your computer right now is a syntactic machine. You can type things into it, and it will manipulate those symbols. It will fix your spelling. But it doesn't know what anything means. It's just manipulating them mechanically. When we study language without paying attention to meaning, we are doing syntax. If we start to include meaning, then we are doing semantics. And whether or not a sentence is true counts as a part of its semantics. Because after all, you need to know what a sentence means in order to determine whether it's true. This means that there are 2 ways of getting at the word therefore, ways of understanding it. We can understand it syntactically, or we can understand it semantically. So if we understand the word therefore syntactically, what we're saying is a conclusion follows validly from a set of premises just based on rules of syntax. If we do it semantically, we say that the conclusion follows validly, and when we prove that, we've taken into account meaning. So we call the syntactic entailment and semantic entailment. What we were just doing now with truth tables is a kind of semantic entailment, because we were showing that a conclusion follows validly from premises by thinking about the truth of the statements. And in that way, we were taking into account their meaning. Now, in the next chapter, chapter 6, we're going to look at a way of showing that arguments are valid that doesn't take meaning into account at all. It's purely syntactic, right? We'll call this syntactic entailment. And then we repeat this whole process for our next language, right? Right now we're talking about SL. Later we talk about QL. And again, there will be semantic and syntactic methods. The nice thing about the logic that we're dealing with is that it turns out that semantic and syntactic entailment are equivalent. If you can prove something syntactically, you can also prove it semantically and vice versa. This is not true for more complicated logical systems. And this is just one of those moments where we begin to run into the limits of logic. So we had different logical properties that we are using to analyze sets of sentences or individual sentences. So for an individual sentence, we can say it is a tautology, a contingent statement, or a contradiction. If we've got two pairs of sentences, we can say that they are either logically equivalent or not. For sets of sentences, we say that they are consistent or not, and for arguments, we say they are valid or not. For each of these, we have tests, right? So if something is a tautology, we say that it has all T's under the main connective. If it is a contingent sentence, it has both T's and F's under the main connective. If it is a contradiction, it has only F's. Okay. If two sentences A and B are logically equivalent, the columns under the main connectives match. If a set of sentences is consistent, there's one row where the whole sentence is true. And if an argument is valid, there are no rows in which the premises are true and the conclusion false. And what we'll see later on is that all of these semantic methods have equivalent syntactic methods, except sometimes you will actually get stuck, and we'll talk about that later as well.